Section: Introduction. In this section, we delve into the comparison between LoRA and full fine-tuning for Llama 27B, and sometimes 13B, models in the challenging domains of code and mathematics. We investigate two training scenarios within each domain: instruction fine-tuning and continued pre-training. Instruction fine-tuning involves question-answer datasets with tens to hundreds of millions of tokens, while continued pre-training entails training on billions of unlabeled tokens. We assess the performance in the target domains using challenging coding and math benchmarks and evaluate the forgetting of the source domain on language understanding, world knowledge, and common-sense reasoning tasks. Our findings reveal that LoRA falls short in code tasks compared to full fine-tuning, but in math tasks, LoRA narrows the performance gap with longer training. Despite the performance difference, LoRA better preserves the source domain performance than full fine-tuning. We analyze the trade-off between learning in the target domain and forgetting in the source domain. For a given model size and dataset, we observe that LoRA and full fine-tuning exhibit a similar trade-off curve. While LoRA tends to forget less in some cases, it can learn comparably in others, particularly in code tasks. Furthermore, we demonstrate that LoRA offers stronger regularization compared to traditional methods like dropout and weight decay. It also provides regularization at the output level, maintaining a diversity of solutions compared to the limited set produced by full fine-tuning. We investigate why LoRA lags behind full fine-tuning and show through singular value decomposition that full fine-tuning induces high-rank perturbations to the base model's weight matrices, contrary to the low-rank perturbations assumed by LoRA. In conclusion, we provide insights into best practices for training models with LoRA, highlighting its sensitivity to learning rates and the impact of target modules and rank on performance. Our key contributions include the superiority of full fine-tuning in accuracy and sample efficiency, the regularization effect of LoRA in preserving the source domain, its stronger regularization compared to traditional methods, the high-rank weight perturbations identified in full fine-tuning, and the sensitivity of LoRA to hyperparameters. Section Summary. In this section, we explore the efficiency of low-rank adaptation, LoRA, compared to full fine-tuning for large language models, LLMs, in challenging domains like code and mathematics. We find that while LoRA falls short in code tasks, it narrows the performance gap in math tasks with longer training. Despite this, LoRA excels in maintaining source domain performance and acts as a strong regularizer, preserving a diverse set of solutions compared to full fine-tuning. Additionally, we reveal that LoRA's performance is highly influenced by learning rates and the selection of target modules, emphasizing the importance of these factors in LoRA training. Section: Background. In this section, we freeze a pre-trained weight matrix W underscore text pre-trained in R caret D times K, and only learn a low-rank perturbation delta to it. We select which W underscore text pre-trained to adapt target modules and the rank road K. By doing this, we train only D times R plus R times K parameters instead of D times K, which reduces memory and computational requirements. For instance, applying AR equals 16 LoRA to a 7B weight matrix with D equals K equals 4096 trains less than 1% of the original parameters. LoRA can save memory and enable efficient multi-tenant serving by sharing a base model across users with personalized adapters. We simplify the search over target modules by grouping them into three classes: attention, matrices, MLP, matrices, and their union, all, for L layers. While LoRA was initially applied only to the attention matrices, it has now become common to target additional modules. We train on coding and math datasets known to improve performance downstream. The datasets include Coding Captain, StarCoder Python, Math Captain, Open Web Math, Coding IFT, Magicoder Evil Instruct 110K, and Math IFT, MetaMath QA. We evaluate our models on various benchmarks such as Human Eval for coding tasks and GSM 8K for math tasks. We compare the performance of LoRA and full fine-tuning after conducting a thorough learning rate sweep for each method. We analyze sample efficiency by computing learning metrics based on the number of training samples seen. In coding tasks, we observe that instruction fine-tuning leads to more significant improvements compared to continued pre-training. The best LoRA model for coding tasks peaks at 16 B tokens with human eval equals 0.175, matching the performance of full fine-tuning with 1 B tokens. For math tasks, LoRA shows improvements but remains less sample efficient compared to full fine-tuning. Overall, LoRA tends to underperform full fine-tuning, especially in programming tasks. Instruction fine-tuning consistently leads to larger accuracy gains than continued pre-training in both coding and math domains. Section Summary. In this section, we introduce LoRA, a method that freezes a pre-trained weight matrix and only learns a low-rank perturbation to it, significantly reducing the number of parameters trained. By targeting specific modules and using low-rank approximations, LoRA saves memory and computational resources. We experiment with LoRA on programming and math tasks, showing that while it underperforms full fine-tuning, it can still achieve notable performance improvements, especially in instruction fine-tuning scenarios. Section. LoRA forgets less than full fine-tuning. In this section, we will discuss the comparison between LoRA and full fine-tuning in terms of forgetting. Forgetting is defined as the decline in performance on various benchmarks like Hella Swag, Arc Challenge, and Wino Grande. We found that in general, incremental fine-tuning, IFT, leads to more forgetting than catastrophic parameter transfer, CPT. Programming tasks induce more forgetting than math tasks, and forgetting tends to increase with more training data. Importantly, we observed that LoRA forgets less than full fine-tuning, especially in programming tasks. In Captain for coding, LoRA's performance remains steady, while full fine-tuning's performance decreases with more data. In IFT for coding, both methods show performance degradation with more training epochs, but at their best performance levels, LoRA outperforms full fine-tuning. For math tasks, both LoRA and full fine-tuning do not exhibit significant forgetting on the open web math dataset, likely due to the dataset's composition of English sentences. We also explore the learning-forgetting trade-off between LoRA and full fine-tuning. We create a Pareto curve by plotting forgetting against learning metrics for different models trained for varying durations. LoRA and full fine-tuning generally follow the same curve, with LoRA showing lower learning and forgetting. However, in some cases, especially in coding tasks with IFT, LoRA achieves higher source domain performance for similar target domain performance, indicating a better trade-off. Furthermore, we examine LoRA's regularization properties compared to weight decay and attention dropout. LoRA proves to be a more effective regularizer, leading to less learning and forgetting. Additionally, LoRA helps maintain diversity in token generations during text generation tasks. Lastly, we investigate whether low-rank training can approximate full fine-tuning in coding and math tasks. We analyze the singular value decomposition of the weight matrices and find that full fine-tuning does not necessarily learn low-rank perturbations. The perturbations in full fine-tuning can be approximated by adding low-magnitude noise to the weight matrix. The rank of perturbations increases with more training data and varies across module types and layers. Section Summary. In this section, we compare the forgetting behavior of LoRA with full fine-tuning across different domains like programming and math. We observe that LoRA forgets less than full fine-tuning, especially in the programming domain, showcasing a better trade-off between learning and forgetting. Additionally, we find that LoRA acts as a stronger regularizer compared to weight decay and attention dropout, maintaining diversity in token generations and providing a compromise between full fine-tuning and the base model in terms of generated text. Section. Practical takeaways for optimally configuring LoRA. In this section, we discuss practical insights for optimizing LoRA. When it comes to tuning LoRA hyperparameters, we found that while it may not completely bridge the gap with full fine-tuning, certain hyperparameter choices are more effective than others. Specifically, we observed that the learning rate has a significant impact on LoRa's performance. By analyzing the learning rate sensitivity of LoRa on different datasets, we determined that the best learning rates for LoRa are 5e-4 for code and 2e-4 for math. These learning rates outperform alternative full fine-tuning rates, which are an order of magnitude smaller. Moreover, we discovered that the choice of target modules is more crucial than the rank in LoRa. Targeting all modules yielded better results compared to MLP and attention modules. Additionally, we found that selecting a relatively low rank, such as R equals 16, while targeting all modules strikes a good balance between performance and accuracy. Based on our findings, we recommend using LoRa for improved fine-tuning, IFT, instead of Captain. It is essential to identify the highest stable learning rate, target all modules, choose a rank based on memory constraints, e.g., 16, and consider training for at least 4 epochs. Furthermore, LoRa has inspired various memory-efficient and high-performing extensions, such as QLORA, Vera, DORA, Chain of LoRa, and Galore, along with efficient inference techniques like S-LoRa. When benchmarking LoRa against full fine-tuning, previous studies have shown mixed results. While some studies indicate that LoRa matches full fine-tuning performance on certain tasks, others suggest that full fine-tuning outperforms LoRa, especially in challenging domains like code and math. It is crucial to carefully compare LoRa and full fine-tuning in different settings and datasets to draw accurate conclusions. Lastly, continual learning on a new domain may lead to a trade-off in performance on the original domain. Strategies like replaying source domain data during continual learning can help mitigate forgetting and maintain performance across different tasks. Section Summary. In this section, we find that optimizing LoRa hyperparameters does not fully bridge the gap with full fine-tuning, but certain hyperparameter choices are notably more effective than others, particularly in terms of learning rates. LoRa's performance improves monotonically with learning rate up to a point where training diverges, with optimal learning rates of 5e-4 for code and 2e-4 for math, outperforming alternative full fine-tuning rates. Additionally, targeting all modules with a relatively low rank, like R equals 16, strikes a good balance between performance and efficiency in LoRa for tasks like IFT. Section. Does the difference between LoRa and full fine-tuning decrease with model size? In this section, we explore the question of whether the difference between LoRa and full fine-tuning diminishes as the model size increases. Previous studies have suggested a link between how effective fine-tuning is and the size of the model. Although recent research has effectively used LoRa with 70 billion parameter models, a detailed investigation into these scaling properties is left for future studies. One limitation of spectral analysis is that while full fine-tuning often discovers high-rank solutions, it does not rule out the existence of low-rank solutions. It simply indicates that they are not commonly found. Another perspective is that the rank required to reconstruct the weight matrix may be higher than what is necessary for a specific task. When considering why LoRa performs well on mathematical tasks but not on coding tasks, one theory is that mathematical datasets have a smaller domain shift, containing a higher proportion of English, which reduces the likelihood of forgetting. Another possibility is that the evaluation using GSM-8K is too straightforward and fails to capture the new college-level mathematics knowledge acquired during fine-tuning.